Okay, welcome back, and we're about to start the third session. This third session of the symposium has to do with the scientific issues that were probably the biggest ones for Sid in his career, namely the structure of the proton and the fundamental interactions at very short distances. You've heard that Sid in the 1950s imagined SLAC in the future as a facility to have elementary particle collisions at energies much greater than 1 GeV. We're now, of course, talking about LHC with elementary particle collisions at energy greater than 10,000 GeV. But nevertheless, the program is somehow continuous. We're going to hear about the structure of the proton, the latest results on hard scattering at the highest energies, and some results about models. About models, there's one anecdote which I actually can't resist telling you. In the physics of beyond the standard model, there are generally two ways people go. One way is supersymmetry, which we've heard a lot about this morning. The other way is the ultimate compositeness of quarks, leptons, Higgs bosons, etc. Sid had a very definite position on this issue. In the SLAC theory bet book, there is the following bet with Sid and two of the most prominent Russian theorists. Lev Okun said, this is the 1980s, at the time of the SSC, supersymmetry will be discovered. Gribov said, at the time of the SSC, supersymmetry will not be discovered. Sid said, at the time of the SSC, supersymmetry will be forgotten. Anyway, we've got that covered. But first of all, we're going to hear about the latest on the structure of the proton, actually using Drell-Yan as a tool to allow the LHC data to improve our knowledge. And we have one of the top experts on that, one of the most active theorists in this area, properly, I think, an intellectual great-grandson of Sid, Lucian Hardy, from Oxford, recently from University College, who's worked on one of the major parton distribution function fitting programs. Thank you very much.
Hello? There we go. Perfect. Yeah, well, thank you very much to the organisers. It's really great to be here. I didn't personally have the pleasure of meeting Sid Drell, but you know, in some sense, I'm applying his work every day of the week. I was kind of thinking it's a bit weird that I've probably said his name thousands of times or written his name thousands of times. You know, it's a sort of unintended consequence of doing well, great work. So yes, in particular, this process here plays a very important role in our understanding of proton structure at the LHC, and that's what I'll be telling you about. So to motivate that, the LHC, the Large Hadron Collider, it's the most powerful accelerator ever built. It's got unique sensitivity to the standard model and beyond it, as we've just heard, and to the Higgs sector. But what it also is, predominantly, is a proton-proton collider, which means that it's a sensitive probe of proton structure. It can tell us about the structure of the proton. And you know, the other side of the coin is that if we're going to understand anything about what we're doing now, we better understand the structure of the proton, essentially as an input. And it's quite nice to sort of base a talk around that, around Drell-Yan, because it actually plays a kind of key, a special role in our understanding of the proton, and you can sort of chart the progress that has been made to the point we are now through that process. And so I'll say a little bit about that. But before that, kind of some preliminaries and building up to that, I'll tell you a little bit about proton structure and PDFs, parton distribution functions. It's perhaps a little bit silly given some of the people who are in the audience to explain this to you, but I think it's worth doing again. You know, the first measurements of proton substructure, direct measurements, were from deep inelastic scattering. You're scattering your high-energy lepton off a proton, and you understand the scaling behavior, the experimental data that came out of that within this parton model. The cross-section is a convolution, a factorized convolution of two things. Our parton-level cross-section, which is essentially the leptons scattering off the parton constituent, the quark constituent here, or the antiquark of the proton, and a PDF, a parton distribution function, which tells us about how these things form up the proton. Or more concretely, at lowest order, simplest approximation, they're just the probability of having the final parton, the quark, the antiquark, the gluon, carrying some Bjorken x, some momentum fraction x within the proton. And there is our final formula there for the lepton-proton cross-section. So going beyond that, there's deep and elastic scattering. That's obviously the first step into understanding these things. I have to mention the pioneering measurements at SLAC. There it is. There's what you expect for elastic scattering falling off with a form factor like a bomb, and there is the scattering off the partons, quite different in behavior, the point-like partons. And now, these days, the state-of-the-art is the Hera collider, the electron-positron-proton collider, where we really have this beautiful high-precision data. And you can actually use that data alone. People do it, so-called Hera PDF, to extract these things, the PDFs, to this level of precision, which is great. But it is an incomplete probe. It doesn't tell us about the complete flavor decomposition. It doesn't tell us about the gluon in all regions. And so we want to go beyond that. So how do we go beyond that? Well, we apply this PDF factorization, this parton picture, beyond lepton-proton to proton-proton, hadron-hadron collisions. And that's where Drell-Yan comes in, because that was really the first thing to consider that, I would say. So here you have, well, this is a Drell-Yan process, a quark and an antiquark here making a W. And the picture is the same. Your proton-proton cross-section is a parton-level QQ bar annihilation cross-section, and the quark-antiquark PDFs. And the powerful statement really is just this, that the thing you extract here is the same as the thing you extract or you measure there. And this is generic. This is what we do at the LHC. Not just to Drell-Yan, but to other standard model processes, jets, TT bar. It's always the same picture. And also, if you want to make predictions for BSM, BSM objects, new resonances, or Higgs, of course, it's the same idea. So the idea is to fit to something like this, perhaps, and to predict for something like this, or something like this. So the kind of logical conclusion of that is where we are today, which is global fits. So we really want to constrain these things as much as we can, over as wide an X region as we can. And the simplest way to do that is to just include as much data as possible into the fit. And so that's what a global PDF fit is. That's what global means there, really. So deep and elastic scattering, fixed target, hadron collider data, very importantly. And there are three major groups that do this: CT, MMHT, and NMPDF. And I am the H there. And I'm not going to tell you about all of the details of how they differ. They differ in their approaches, how they fit the PDFs, the data they include, and so on and so forth. But the fundamental idea is the same. So a couple of things which are kind of nice to point out about that. Here is a list of all of the data that went into the MMHT14 fit. You're not supposed to make out what these are. Just each of these is a different data set from a different experiment, going from basically low to high energy. And if you look here, I've blown up the total chi-squared per point, leading, next to leading, and next to next to leading order. And what you can see is over all of these experiments and over all of these energies, you've actually got a chi-squared per degree of freedom of order 1, which is pretty impressive, I would say. And also it actually improves as you go up in order, which is also encouraging. And here are the sort of PDFs we extract. You have the valence structure, and you have the C and the gluon as well. So why do we care about these things? Why do we care about, well, extracting PDFs precisely? Well, really our knowledge at the LHC is limited by our knowledge of PDFs. So a few examples. Classic thing, if we're going to look for BSM, is to use the extended energy reach of the LHC to look for high mass objects. High mass is exactly high X, so here are the gluon luminosity is the combination of the gluon PDFs at fixed invariant mass of the thing you're producing. And as you go to high mass, that's exactly where the gluon is less well determined. So you can see that the uncertainties, these are the uncertainty bands on different global fitters. You can see them diverging and blowing up. So we want to constrain those things more to tell us, to set limits or tell us about something if we saw it. The Higgs coupling as well, of course, we want to measure its coupling to standard model state as well. And again, if you want to do that, you need to understand how it's produced, and that plays an important role. And finally, precision standard model measurements. The W mass is really the most classic one for that, because really, actually, the PDF uncertainty, these are the uncertainties on the latest measurement. The PDF uncertainty is biggest one. So that's something we really want to get down as well. So where are we? What I've shown here is it's not my plot, but it's the amount of data collected with year from the LHC. Now, some of that is to be collected because it's in the future, but some of it has been. There's the Higgs being discovered, there we are. And this is all approved. This is the high luminosity LHC running. This is all going to happen. And so it might seem like we've already got quite a lot of nice data from the LHC, but we're actually in the foothills of it. You know, there's going to be a load of high precision data to come. And so, of course, we want to take advantage of that. On the theory side as well, and this is all going to go into our PDFs, as we'll see, there's also been an explosion in precision, if you like. So this is a classic plot which shows each of these is a calculation, QCD calculation at next to next leading order. You can see you sort of potter along a bit for a few years, and then some various bottlenecks get broken, and suddenly it's become basically the standard. And this gives a lot of opportunities for us, but also some challenges. Okay, so having motivated that, I'm going to go back in time again to Drell-Yan and chart the progress through that. So here is the original paper. It was really it was great to give that a close reading when preparing for this talk. It's a really nice short paper. I'd encourage you to have a look. And it's all there. Here is the Drell-Yan process, a picture for it, QQ-bar annihilation, here to make a mu plus, mu minus, but they discuss various final states, for example, via a lepton and a neutrino, for example, which is the other classic one we do at the LHC. And here is a formula which essentially you could recognize as something like what we use now, not quite in the same way. And there was even the first numerical prediction for Drell-Yan there, which they made. And they even discussed the steep fall off you get with invariant mass, which is actually being driven by, they don't exactly use this language, but it's being driven by the PDFs falling off as x goes to 1. And you know, that's something we contend with at the LHC when you're trying to push to high mass. So you can even see that here. And in the opening paragraph, in fact, they had this nice sentence: nucleons are the partons of the nucleus, and the partons of the nucleon itself are still to be deciphered. Which I think at that time they were still working QCD out, so it kind of meant in a very literal sense, but still it's kind of a nice message when you think that this was really a crucial step into deciphering that. So, of course, it's never just theory. At the same time and afterwards, data came along, fixed target data. And that was what's interesting, actually, is that it didn't agree that well. So this is one example, but there are many. There's the data you can see there, and that solid line is the parton model prediction. And you can see the data clearly overshooting the theory, and the dashed line is then scaling the data up by a fudge factor, a k factor of about 2. And here's a list of different such k factors for different experiments. So what's happening? Well, the point is this was a leading order prediction. And then by the late 70s, the full NLO corrections were known. You look at these sorts of processes, these sorts of diagrams, and they were known to be sizable. And so the k factor, the NLO to leading order ratio, was about 2. And so indeed, the agreement became much better. The apparent discrepancy here is resolved. So a first indication of the importance of precise theory. So what about PDFs? Well, fairly soon after all of that, people started to think about using Drell-Yan to extract PDFs. Basically, the first global fits, in fact, really, the fact that they included this was what would allow you to label them as a global fit. So really, the first global fits included Drell-Yan data in the early 90s. They used NLO theory, first fixed target, but actually quite soon after the data from the Tevatron. So there is some Tevatron data for a lepton asymmetry, I think. And you can see the PDF fit to the data is pretty good. And similarly here, this is for some fixed target data. And there are the PDFs they extract. So it's really was placing important constraints on proton structure, and proton flavor structure. So now we're kind of going forward in time. Well, you can tell because the plot has become color. So it's a nice, actually on the theory side, right? The first hadron production observable to be calculated full stop at NNLO was the total Drell-Yan cross-section in the early 90s. And then 10 years later, differential in rapidity, the calculation came. And this is a very nice plot showing that. You have the leading order prediction with the the uncertainty band, the theory uncertainty band. You see that jump as you go to NLO, smaller uncertainty band, and then as you go to NNLO, it's converging nicely, and actually you can barely see the uncertainty band. It's 3% level precision. And these days, we've got Monte Carlo generators, Fuse, DY, and NLO, and other ones that actually do this whole thing, and they include the decay of the W or the Z with full spin effects. So you've got something that you can directly compare with data. And so we can do that now. So using those tools at NNLO is really the standard for PDF fitting. So it's a very precise probe. And here we are in the LHC era, and you can see, I will go into some more detail about these things, but the lovely precise data on Drell-Yan that's now coming out of that. So before moving on to that, and I can't take credit for take credit for making this plot, but for not having the idea of it. It was Lance Dixon who pointed this out to me, that actually you can chart the progress in a different way. Well, okay, so if you look at how many citations the original paper has, as of yesterday, maybe it's been cited today, it has 1,448 citations. But we shouldn't compare against a single number as physicists. We should go differential, so that's what we do. So this is sort of, I don't know, D citation, D year plotted. And what you can see here is that it's dangerous for it, because it's become a classic paper around here. And now people are thinking, well, I probably don't need to bother citing it anymore. And it has a kind of wilderness where maybe they cite the NLO papers or the NNLO papers. But what's really interesting in all of this, and why it's worth plotting it, is that second peak there. And what's happening there is that's exactly coinciding with when the LHC turns on. So it's data. It's you look at, well, who's doing those citations. It's the LHC experiments, but it's also theorists who are kind of thinking about new things because of that new data. And yeah, insert your own joke about new resonances with the LHC and whatever. I won't do that for you. But it's really playing a key role in Drell-Yan. You know, it shows the key role that actually the LHC is playing, well, that Drell-Yan is playing in LHC physics. So let's say a bit more about that. Well, first of all, what can it tell us? I've kind of mentioned this a little bit, and it's maybe sort of straightforward that you're colliding a quark and an anti-quark, so it's telling you about the flavor structure. Kind of the important point is that in DIS, you're also, of course, sensitive to quark distributions, but in a different combination. So the fact that you've got the Q and the Q bar annihilating tells you something different, complementary about how those things are making up the proton through these various channels. So depending on the kinematics, it might tell you about the U and D valence, or the U bar and the D bar, or it might also tell you about the strangeness as well, which is less well determined. So a few examples of that, and what data is now telling us. This is a really nice example, Atlas data, fairly recent, of W and Z production. This is at 7 TV in 2011, but it was only released last year because it took 6 years to really understand the systematic errors as much as possible and release this data with these percent level experimental uncertainties on them. And this was now precise enough to tell us something about the proton strangeness. So you can look at the strangeness ratio, S plus S bar over U bar plus D bar at some scale and some X. They just kind of pick at random. But the point is that previous global fits preferred something about 0.5, so some amount of suppression in the strangeness, and they prefer something of order 1. So we've included that in the fit. So here's the same observable, but at the same scale, but versus X. This is our previous PDF fit, so living down here about 0.5, quite big uncertainty, or very big uncertainties. Now you add in that Atlas data, shift it up, and you get a smaller uncertainty. You can really visually see the impact it has. So you can do more than that. You can go double differential. Again, it's using all of the data that we have at the LHC to go as differential as possible over as wide a region as possible. So the point here is that the parton momentum fractions are related, of course, to the invariant mass and the rapidity of the lepton system. So that if you go to high invariant mass, you push to high X, and if you go to high rapidity, you're sensitive to both high and low X from the two protons. So CMS have indeed released such data, double differential in both rapidity and invariant mass, where over a very wide mass region, 15 to 2000 GeV, this is at 8 and 7 TeV. So what does this get you? Well, you can go to below the Z peak, and then you've got a photon dominantly coupling, so that gives you different combinations of the Q and the Q bar. Or you can go to high invariant mass, and there that's telling you about the Q and Q bar actually at high X, which is actually exactly in the region where they're poorly determined. And you might need them as an input, for example, for BSM physics. And something, well, it's not really Drell-Yan, but it's close to my heart, which is that you can also become sensitive to photon-induced production, gamma-gamma to L plus L minus, which has the same final state. So here is this beautiful plot, invariant mass distribution, it's the Z peak, and you go double differential. You break it up into mass regions and look at the rapidity, and that gives you nice differential information about the proton structure. So as well as going double differential, you can go forward. So LHCb as well are very much involved in this. This detector, with its forward acceptance, which is geared towards B physics, of course, but it gives you, almost accidentally, a really nice probe of both low and high X because of that. So it has a pseudo rapidity from 2 to 4.5, which is exactly pushing beyond the region that you have for Atlas and CMS, which sits centrally. And this, as I say, gives you access to low and high X, where actually things are, again, less well understood. So here is that. Here's a W invariant mass distribution with rapidity, and again, similarly for the Z. You can see the nice precision and the comparison against different PDF fits, and all of this is included in the latest fits. Okay, so kind of summarizing that in a way. So this is actually a working group. Well, this is a slide from the working group 1 summary talk from Deep and Elastic Scattering last year, which was very much a conference that's populated by people who work on these sort of things, if you're not aware of it. These are the 3 global fitters, and these are lists of LHC data. And you can see Drell-Yan is prominent in there, that are included in these fits. And it's not just superficial. This is really one of the most constraining data sets now. It's really playing a major role. But so Drell-Yan's not the only thing, so I thought I'd tell you about a little bit else about what's being studied, give you a few brief examples of that. So one nice example, which I think John will talk about a little bit more, is jet production. Here we of course, at the LHC, it's dominantly gluon initiated as opposed to quark. And the point here is that now the momentum fractions carried by the gluons are related to the PT of the jets you produce at leading order. Which means if you go to high PT, you push into the high PT tail, you're sensitive to the gluon at high X, again, where it's less well determined. So it's a very nice thing to do. And again, it can have impact, for example, for BSM. So this really is playing a crucial role as well. And moreover, harking back to that slide I showed a while ago, we have an NNLO calculation for this, which has actually quite recently been completed and was a very long project, lots of work going into it. So we have a combination of high precision data, high precision theory. And of course, the natural thing to do is to say, what does that tell us about the proton? So we've gone away and included that in a fit. I won't go into all of the details, but basically we go up to NNLO, we use the NNLO theory, we include Atlas and CMS high precision data, and a few things which you can point out. So number one is this is the chi-squared for Atlas and CMS data and different jets, radii, and you go NLO to NNLO, and you can see the improvement across the board. So perturbation theory is working as it should, which if you've spent 6 years of your life, like James Curry or Nigel Glover, calculating this is probably, encouraging. If it was the opposite, it would be very discouraging, I think. And you can, there's various other more technical things. So you might worry, well, there's different choices about different jet radii. You can also take different choices for your factorization scale. What if these affect the PDFs in some major way? And that would be a worry. But actually, things are pretty stable with respect to that. So this is the gluon, the baseline without jets and the uncertainty band on that. And I've just shown the central value for some of these different choices. And you can see the kind of stability and the impact it's having on the gluon as well. And I've not shown the uncertainties here, but those also go down. So you can see the impact that's there. Another nice example, using the top quark as a probe of the proton, which maybe seems a bit unusual, but it's very, very actively being pursued at the moment. So glue-glue to TT bar. And the idea is the same. Right? You go to high invariant mass of the TT bar, high PT at the top, again, that probe's high X gluon. So it's kind of complementary to jets, if you like. And again, it's the same story. we now have a recent NNLO calculation of this. So we have this combination, again, of high-precision data, high-precision theory. So here, indeed, so the data is now becoming statistically precise enough, if you like, to go out to high PT. There's some data from Atlas and CMS and various NNLO predictions, and there's definite room to include these in fits. So NMPDF and collaborators have done that. They consider the impact of this data at 8 TeV with the NNLO theory. I would just point you to this plot here, actually, which shows the gluon-gluon luminosity compared to their baseline, which basically has no TT bar data. And there it is with the top quark differential data. And I mean, you can see by eye the impact it's having, pulling, it seems, in the same direction as the jets and the reduction in the uncertainties. Okay, well, back to Drell-Yan in a way. It's this kind of extended Drell-Yan family. Lots of other processes are being studied, but here are a couple of nice examples in that family. Well, okay, Z boson, it is Drell-Yan, but you go to the high PT tail of that, so the Z is now recoiling off a gluon, and that can actually tell you something about the gluon PDF as well. And again, we have a new NNLO calculation of that, and there have been studies pursued in that vein. I talked about strangeness. Well, there's another more direct probe of that, which is W plus charm. So these sort of diagrams here, where you look for a W in association with a charmed hadron, and you can see that one of the dominant things is going to have an S in the initial state. So it's quite directly sensitive to your strangeness. And there's some interesting data coming out of that. The Atlas data seems to push in the same direction as their Drell-Yan. The CMS maybe slightly differently, so maybe some things to resolve, but it's interesting to see where that goes. So where do we stand? What I've plotted here is a couple of examples, not quite at random, but just to give a selection. What I've got here is the three major fitters. The gluon with their PDF uncertainty bands relative to the MMHD baseline. So sticking with the gluon, I mean, it's probably a bit difficult to make out around here, and that's sort of the point. They are pretty consistent. And we're at a stage where we've got kind of 2% level uncertainties at scales relevant for the LHC. But it's not all consistent. And you can see, if you look closely, that, for example, NMPDF are kind of pulling outside. And actually, they are exactly the more recent set, which includes more of this LHC data on, for example, TT bar. So we can expect, and we'll expect updates from us and from CT soon, which include that data. They may well move in the same direction. Things are not, it's not all as well constrained as that. If you look at something like the D bar, which is less well constrained, roughly consistent, but clearly bigger uncertainties. And in particular, as you go to high X, things start to vary more. You start to become more sensitive also to methodological differences in how you do the fit. So things are looking reasonable in terms of their agreement, but there's clearly work to do. So we can look to the future. It's not just about sort of fitting data and fitting more data, actually, and we're already coming to the point where we need to start asking new questions if we're really going to use this data in the best way. So in the high luminosity LHC, that's this running up here, yes, we can ask, or how precisely can we expect to constrain PDFs in the future with all of this, and we're looking into that. But we also need to wonder about new questions, so things I've not gone into here in any detail at all, or indeed at all in some cases, but which people are very much actively thinking about. Well, if you're going to worry about high precision, what about electroweak corrections? What about theory uncertainties? The uncertainty in the fact that you're using perturbative expansion for your theory to extract your PDFs, that's usually not included. In fact, it's essentially never included, so how would that be done? Resummation. There's some nice recent work on the fact that we're actually going to lower X, we're becoming sensitive to lower X as you go forward in rapidity, for example, and that maybe you need to include that in your PDF extractions. And indeed, actually, a bit more speculatively, is the idea of perhaps running for high energy LHC. So same tunnel, but 27 TeV. And now, again, you can ask questions. Well, again, we're going to be going to lower X. We'll have a higher Q squared reach. And there's a whole set of questions we'll need to think about there, and opportunities as well. And so there's been a nice workshop on that, in fact, quite recently, discussing those issues. Yes, I couldn't give this talk without at least a plug, which is to a recent review I was involved in with Jun Gao, who's from CT, and Juan Rojo, who's from NMPDF, about the structure of the proton. So if you're interested at all in anything I've had to say, there are many more details to be found here, and there's the archive link. Okay, actually I'm coming to the end. Well, if you could to summarize my talk in 2 bullet points, that would probably be it. It's, Drell-Yan has really played a key role in our understanding of the proton structure, from the early parton model, but I hope I've convinced you right now, right to the present day with a high precision LHC era. And there's going to be a great deal more to come, and you should stay tuned for that. And actually, if I was to summarize it without words at all, but in figures, I think perhaps these 2 figures would also do the job. So here is that original mass distribution from the first Drell-Yan paper. And there it is. And even by eye, the comparison looks pretty good, going from left to right. There's the CMS data, beautiful data over a huge mass region. This is sitting just over here. And this isn't going to be the end of the story. So going off stage, there's going to be many more, much more beautiful data to come, and also theory to follow it, hopefully. Thank you for listening. Thank you.
The next speaker is John Butterworth from University College London. John is a longtime campaigner in elementary particle physics. He was at Petra, he was at Hera. Lately, like the curve of Drell-Yan citations that you saw on the previous slide, he's become much more prominent due to his recent role in the LHC, where he's been one of the leaders in a new subject in Hadron Collider physics, namely jet substructure, which has been an amazingly useful tool in exploring both standard and non-standard physics at the LHC. So John will talk about the current status of Sid's dream of seeing elementary collisions at the highest possible energies.
Okay. Thank you, Michael. Thank you very much for the invitation. So yeah, I'm going to talk about quark and lepton scattering. That's quark and or lepton scattering. We'll cover all combinations of that at the highest energies. I realize this is the second talk after lunch, so I apologize for hitting you with such a technical slide so early in the talk. But maybe it's worth just remembering that this is the landscape we're dealing with. This wasn't clear when Sid Drell was doing his work, but it is clear now that we have a standard model with 3 generations, 6 quarks, 6 leptons. And this standard model, these are the players, if you like, in the high energy collisions that I'm going to be talking about. It claims to cover a huge range of phenomena. You can argue about where exactly what we mean by the mass scale on each of these, but this is a mass scale, or equivalently a distance scale, covering observable phenomena. And the region, and we've already heard today about very low energy effects, very small corrections that also then have reach up to very high energies, because the standard model is so powerful in the diversity of scales it can address. What I'm talking about really is this region. So from the point where, I guess, quarks stop being confined inside hadrons and start becoming treatable as partons and as elementary particles, visible as elementary particles, up to the kind of, well, as far as we can go, which at the moment is defined by the Large Hadron Collider's center of mass energy, I guess. And somewhere in the middle of that is the electroweak symmetry breaking scale. So that's really that. I'm going to take you on a stroll through this region of physics, which is it's kind of also where Lucian's parton density work is taking place. And the start of that really is down to what we call hard QCD, the strong interaction. This property of QCD that it has asymptotic freedom, so at short distance scales, this is where we leave quark confinement behind as we go above the lambda QCD scale of QCD. We go to higher energies, the strong force becomes weaker, and this is a compendium of measurements of alpha S, the coupling constant, and you see indeed It's fairly, the perturbation series doesn't converge so quickly when you have a coupling constant of 0.2, but as you go up in energy, the coupling becomes weaker, and until in the end, at the very shortest distances, the quarks are effectively free. And we have many ways of looking at that, and one of them is the probes in deep inelastic scattering that Lucian was just talking about, but another one is the fact that the diagrams, that essentially quarks and gluons make a break for it, and you observe them as jets. And Lucian also mentioned these jets. The idea is that the short distance physics, where the quarks and the gluons are asymptotically free, determine the bulk kinematics of the collision event when you collide, in this case, electrons and positrons together. And this kind of event is understood in terms of a QQ bar production from an annihilating electron-positron pair with the radiation of a gluon, and the probability of that radiation is proportional to alpha S. And you see this kind of Mercedes-like events. This is from the Petra collider in here, and this was really the first direct evidence that the gluon existed. These quarks are essentially, these jets are essentially when quarks or gluons make a break for it. The idea is the kinematics are determined by the short distance physics, and then in the end, because they are confined at lower energies, you end up with a spray of hadrons that reflects those kinematics. And we still do physics like this at the Large Hadron Collider. This is a detail of an Atlas event display from the Large Hadron Collider, very high energy jets, which will be appearing later in this talk. And again, you don't just have the initial hard scatter and then soft physics, you have possibilities of hard radiation inside the jet, and I will come back to that later in the talk as well. But for now, just to show some data early on from Atlas, this is data from run 1 still. It's ATV collisions from 2012, 13, and 2011 and 12, sorry. And you see each one of these arrays of points, they're all scaled by different factors just to get them on the same plot. But essentially, you're looking at a transverse momentum of the jets here in the range of 70 GeV up to 2 TeV. And each one of these is a different rapidity bin, and also on there is a next to leading order QCD calculation, not the next to leading order, which is now available, that Lucian showed for some distributions. But again, you see that we're really studying high energy quark and gluon scattering up to well above the electroweak symmetry breaking scale. Stepping back from the LHC for a moment and just going up in scale from the quark confinement, where jets become defined, up towards the electroweak symmetry breaking scale. This is a plot. I did my, as you heard, I did my PhD and postdoc on Zeus, and I feel duty bound to show this plot every time, even though Lucian has already shown lots of HERA data. Because this, to me, this is the motivation for building the Large Hadron Collider in one, really, without reference to any theorists at all. No offense to most of the audience, I guess. But you see here the neutral current cross-section and the charge current deep inelastic cross-section coming together at the electroweak symmetry breaking scale. Obviously, a weak scatter is much less likely than an electromagnetic scatter at kind of everyday energies, but as you go up in energy scale, they converge. This is, in a sense, electroweak unification, although, of course, the gauge groups are still the same. And this is understood in terms of the mass of the propagators here, of course. So this is the electroweak symmetry breaking scale. It's intimately connected to the mass of the W and the Z boson, and therefore to the Higgs mechanism, and understanding all of that within the standard model. So this, to me, this tells you that it's worth building a collider that can get you above this region anyway, even if you didn't have the theory curves on here. You can see that the data come together. So, of course, that electroweak symmetry breaking scale is around the mass of the Z or the mass of the W. And just stepping from lepton quark scattering to E plus E minus annihilation and back again, you see here the E plus E minus cross section with the very, very clear Z peak. This is from LEP1 and SLC that we're doing this, and then LEP2 going above and starting to produce W pairs. Again, around and above the electroweak symmetry breaking scale, and one of the key results from that needs to be mentioned is one of the things we've learned from lepton and quark scattering in particular is that if you produce a lot of Z bosons, you can measure the width, so the cross-section, essentially production cross-section as a function of the center of mass energy there, and you can measure that in a visible channel, such as muon, Z decaying to muons, or Z decaying to electrons. But that width is sensitive to all the decay modes of the Z. And that then tells you that because the Z couples weakly and decays to neutrinos, that tells you how many flavors of neutrinos it's got, and therefore tells you, back to this technical slide here, actually how many generations we have, which is the first time we really could constrain that and really set the stage for the standard model here. So now it's obviously possible that you can have fourth, fifth generations, but if they're there, then they're very, very different from the ones that we have now. They do not have light neutrinos that couple to the Z. So a breakthrough result just before the electroweak symmetry breaking scale, if you like, or around it. And this was this is an example of the huge amount of precision theory and experiment that's gone into measuring the phenomenology of quark and lepton scattering. And this is kind of where we were pre-2012. So this is that standard model slide with a significant omission, of course, because this is really where we were in terms of what we knew from the data. So we knew there were 3 generations, we knew the fundamental forces, and we were making plots like this. So this is, if you like, the least constrained and most powerful constraining consistency check between standard model parameters. We've got the mass of the W boson here, the mass of the top quark here. They have to, the electroweak corrections, the loop corrections that go into the theory tell you that there's a very powerful consistency check here. They constrain that if you fix the mass of the top and the mass of the W, they have to relate to each other, and most particularly, they require the presence of the Higgs boson within the standard model. And this is where we were literally in March 2012, which of course is a significant date, where the LHC had been running for a while, had got some of its first results. LEP had ruled out the Higgs below about 114 GeV mass. The Tevatron had actually just encroached on that and actually just ruled out the 114, 115 itself, literally in this conference where this slide was shown. And the LHC and the Tevatron had been biting into chunks of possible mass windows for the Higgs up here. And I remember this as being really quite exciting, right? Because if the Higgs was not found within either this grey band or this grey band, that basically meant the standard model was wrong. Of course, that's why we built the Large Hadron Collider. It could do that and study that. You've already seen this plot on this picture on one of Lucian's slides, and I think given the title and the subject of this conference, you have to show this kind of plot, which is giving you the reach of. This is a plot. This is the Drell-Yan process, of course, proton-proton going to 2 leptons, with all the structure of all the meson resonances and then the Z boson here. It's a beautiful plot. We tend to show it, and there's also an atlas version, which I'm probably contractually bound to show. It's a beautiful plot to illustrate the understanding we have of our detector. But you'll notice it's a log scale in energy, so it really undersells the center of mass energy reach of the Large Hadron Collider. Much better at doing that is, again, this plot that was the plot Lucian finished with, where you see that we're really now taking the Drell-Yan process up above the TeV scale and really reaching into electroweak symmetry breaking, above the electroweak symmetry breaking scale. So this is what we get. This is not really Drell-Yan. What's going on here is, well, you'll see when I show the diagrams that some of it is in principle part of the Drell-Yan family. But this is just counting the number of 4 lepton events observed at the Large Hadron Collider over the dates that are clocking through here. You've probably seen this before. I think it was actually shown by the Nobel Prize Committee at some point, this animation. But you see that we've got all kinds of structure in here, which I'll go into in a moment. But we have one bit of structure here that isn't described by the Higgs-free background. And if you put a Higgs boson in, you can model it fairly well. And so this picture becomes this picture. We know that the Higgs mechanism, or the Brout-Englert Higgs mechanism, works, and the Higgs boson is there. I'm going to return to that plot that I showed in an animated version. This is a much less kind of attractive or illustrative version than that animated GIF I showed, but to me this is one of the most beautiful plots really to come out of the Large Hadron Collider. It's the same distribution. It's the mass. It's a 4 lepton invariant mass. So, and you can't really, because it's binned now and corrected for detector effects, you can't really see the flow of the data in the same way. But look at the structure here. You've got 90 GeV, you've got the Z to 4 leptons. That's an electroweak radiative correction to the Z to 2 leptons. You've got a continuum background under the whole thing. You've got the Higgs to 4 leptons here. So this is the continuum background here. You've got and another one here. You've got the Z to 4 leptons, which is the 90 GeV peak. And then here you've got a gluon fusion to a Higgs boson giving you this peak. And then you have this sudden dramatic kinematic threshold, which is from when the 2 Z bosons can be on shell. So a big enhancement in the cross-section, which can actually be used then to constrain the width of the Higgs boson, and then back to the continuum there. And I think, this is such a counterintuitive plot, and we would, what also tickles me that we would have made this plot, if we had this collider, we'd have made this plot. It's one of the first plots you'd make anyway. So the Higgs to gamma gamma, we would, without very strong theory motivation, we would never have measured it that well and that precisely, that quickly, for sure. This plot, the 4 leptons, it hits you in the face. The Higgs is just there. You can't evade it. You would have seen it. And that's essentially, it's interesting whether you call this part of the Drell-Yan family, given it's a gluon fusion, but certainly in the mix there of the Drell-Yan type processes. So that was a discovery. We moved on now to doing precision Higgs physics. I'm showing here the run 1 results simply because Atlas and CMS, I wanted to show a combination of Atlas and CMS. We already have many results from the 13 TV running, but we haven't got to the stage of combining the 2 experiment results now. But here you see, for example, the masses from run 1 measured from the 2 most precise channels, the Higgs to gamma gamma and the Higgs to 4 leptons, and their consistency there. Here you see all the different production and decay modes measured as ratios of each other, all checking out with the standard model within the kind of level of uncertainty that we have. So that's a real qualitative change in our understanding of the standard model of physics above the electroweak symmetry breaking scale. We're in a qualitatively new region now, going up to the TV scale and beyond. So to say something about what that, of course, going into a qualitatively new region brings its own challenges. And what we need to exploit these data are essentially precision theory, exclusive calculations, fixed orders, and resummed and matched calculations. Now, the fact that I have to go through that long list of things we need means that there isn't another thing like that 4 lepton peak that has jumped out at us already, because to be honest, if we'd have seen that, we would maybe not be talking about the precision theory in the same way, or we would be worrying about what what theory was that we should be using. But these are the kind of diagrams that we have. We have very high multiplicities of final state particles, but we have they're all taking place in the region where perturbation theory works, where QCD is indeed asymptotically free, so they're indeed calculable, and this is this next to leading order explosion that Lucian showed, that we have these. And the reason we want to do this is, from an experimentalist point of view, is that we don't want to just measure total cross-sections. We want to actually measure the kinematics of what we're seeing when we collide particles in the TeV energy reach. And it's not as simple as you might necessarily think. We have each vertex brings with it, and it's a bit funny as an experimentalist giving this kind of noddy explanation in this audience with some of the people here, but never mind. That we have each vertex coming with alpha S with a coupling. We also have then soft or collinear enhancements in the kinematics as you get within the regions of, say, jet cones here, where you end up with a kinematic logarithm of some ratio of scales, which can essentially be of an order of magnitude, which is enough to cancel out the alpha S, so you end up having to resum and exponentiate these things. And the low X terms that Lucian mentioned are one of the possible resummations, but there are others. You have collinear resummations and threshold resummations that have to be done if you want to fully understand the final state to the level that the experiments can actually measure it and exploit it. And you then also still need to include, for the ones that are not in those these enhanced regions, you still need to include the fixed order perturbation series. This is immensely technically challenging. There's a whole industry of theorists working on producing these calculations in an exclusive way such that they can be compared to the data. And here's an example of one of these. This is this kind of diagram, which again you could say maybe it belongs to the Drell-Yan family. There's a W boson being produced in here along with a lot of jets against which it will recoil. And this plot here is a jet cross-section. It's the transverse momentum of a jet, of one of these jets produced in a W plus jets event. And it agrees pretty well with these various implementations of QCD electroweak available in these exclusive calculations that we can compare to in Atlas. Now you may say, oh, it's okay, this is I don't know, it's at a 10%, 20% level of precision. Why is that so impressive? Look at this. This is the 5th jet in one of these events. So the other 4 jets and the W kinematics are calculated and measured more precisely than this. This is the least precisely measured, lowest PT jet in the event. The jet is spanning the region from 30 up to 150 GeV in PT, and lo and behold, QCD and electroweak theory with the appropriate treatment of these different contributions, can actually describe it rather well. That's on the positive side of the marketing. This is maybe the negative side of the marketing. This is the invariant mass of two jets in those events, and they're the different approximations to QCD. Don't agree so well. They're within uncertainties of each other, but those uncertainties are getting larger. And these are not PDF uncertainties in this case, mostly. They're uncertainties in the treatment of the resummations and the treatment of the higher order corrections. So there's a lot of work going on in this area to do this, and it's important to fully exploit it. This is a kind of fairly famous, from Frank Krauss, fairly famous diagram of what's actually going on in some of these calculations. You have to match the hard sub-process, the short distance asymptotically free physics, the QCD radiation, which is perturbatively calculable if you do the job properly, and you have to match those together, and then you have to somehow build hadrons and final state particles out of these. This is diligent work trying to make the standard model really describe the particle final state that we measure in ATLAS and CMS and LHCb. But it's not just, and it's fun, as I said earlier, it's fun adding the extra decimal point. It's maybe fun adding the extra vertex as well sometimes. But it's not just fun, it's also extremely important if you want to actually untangle the physics of the Higgs sector and the TeV energy scale. What I'm showing you here, for instance, is as we move into the unknown, we're kind of we're making well-defined, precise measurements and calculations of high multiplicity events and high boosts. This is an example of a jet multiplicity measurement in Higgs to gamma-gamma events. Okay, you say, well, why do you need to know how many jets are produced along with your Higgs? Well, if the Higgs is produced from gluon fusion, you get certain predictions for the jet multiplicity. If the Higgs is produced from vector boson fusion, from weak boson fusion, then you get different expectations of the jet multiplicities. If you want to disentangle those to test the standard model predictions and to look for possible contributions from beyond the standard model physics, then understanding the jet multiplicities and distributions in those events is absolutely critical, and that's why you need this whole technology of turning it no longer good enough to have an inclusive calculation. You need an exclusive calculation that you can actually compare to the final state that's measured in the experiments, and that's what these programs are delivering for us now. And then finally, this is something here that another new feature of physics beyond the TeV scale is that we have such a wide phase space, open to us now, that we're well above the mass of the electroweak scale objects, so they're produced with high Lorentz boosts. So you have this is a qualitatively new feature of doing collider physics above the electroweak scale. We have perturbative QCD operating between about 1 GeV, or lambda QCD, the mass of the proton, wherever you kind of think this scale really lies, and it's at some level process dependent. But we have it operating from the start of that point, for around 1 GeV, all the way up to whatever the kinematic limit of your collider is, and at the LHC, that's several TeV. And so if you consider the highest PT jet, it's not just the direction and angle of that jet that are now determined by the short distance physics, it's actually the substructure of that jet. I noticed the title of this session was actually Substructure, and the next talk is about substructure, but I don't think you meant jet substructure, but this is what we're going to talk about now. So that can happen, and in fact you then will get electroweak symmetry breaking scale lies within the evolution scale of the jet from the high energy initiation down to evolving down to the hadronization scale. So you have electroweak physics going on inside your jets. You have collimated decay products from electroweak scale objects, the Higgs, the WZ, the top, possibly other exotic particles if they exist. And we need to account for this and exploit this, in fact, in measurements and searches. I'm just going to show one example of what's really being done now, again, because I think it's the right way to do measurements, and it's really beautiful. This is the top transverse momentum, and it's the top transverse momentum special in two ways. One is that it's not a parton. It's the top measured in terms of the lepton, the missing energy, the jet, the B jet. In fact, in this case, it's the fully hadronic top, so it's the hadronic decay of a W. So it's the top measured in terms of final state particles, rather than extrapolating back to the short distance physics with the model dependence that implies. And also it's a top that's highly boosted, so it's reconstructed within a single jet, and you're using QCD knowledge to decompose that jet and show that there actually indeed was a top in there that the mass of the jet matches the mass of the top, and the internal characteristics of the jet are what you'd expect if you have a top decay to a W and a B, and then a W decays to hadrons. So there are many measurements like this, and searches being done now, which I think very exciting, and are something we're going to see more of as we go into the high luminosity LHC. They'll be even more important at the high energy LHC if that happens, or any future collider with higher energies. Okay, so I started with this slide. The standard model is triumphant at the Large Hadron Collider. It's triumphant above the TeV scale. Everything in the universe is made of this, and this stuff is not made of anything else. It's fundamental. That's clearly nonsense, of course. Gravity doesn't fit in here at all. That is supposed to be Newton and an apple. It's not that clear. And even if we hand over responsibility for gravity to general relativity and forget about all the business near black holes and things, then we're still in trouble because we don't understand the rotation curves of galaxies unless we either modify gravity or more commonly appeal to the existence of dark matter, which is beyond the standard model. So the business of high energy scattering of quarks and leptons continues. Remember, we're in this region here. We're trying to extend it up here. This is deliberately fuzzy as to where exactly we are. But the key point is we don't actually know. In principle, now we have a standard model that can claim to operate up here, but we have no experimental evidence for that. You've heard several talks today of how you can lever yourself up there from low energy measurements. The LHC is kind of bludgeoning at the door with its increased luminosity and possibly at some point increased energy. But as we do that, we need to carry on making these precision measurements, making the precision calculations to go with them, because really we don't know what's out there. Thank you very much.
Are there any discrepancies at all?
Not significant ones. There are, of course, discrepancies. I think that the most interesting ones at the moment I didn't really discuss here because the topic of the talk was supposed to be focused on high energy collisions of quarks and leptons, but the most discrepant measurements at the moment are actually from LHCb, and they're in the lepton flavor violation measurements. Those are, I mean, they're discrepant enough to be of interest. They're not yet, I would say, they're not, obviously not definitive yet. That's very interesting to measure. CMS and Atlas, as I'm sure you're aware, have had various bumps and jiggles in the data. I didn't show any of them because at the moment they're either not public or they've gone away. And I'll leave you to guess what the balance between those two things is. But there's nothing I'm allowed to say at the moment, and there's certainly nothing, I'll tell you now, there's nothing that's totally significant, although there are many plots that we lose some sleep over. And some of them, like the 750 GeV bump, became public, and then we lost sleep over it, and then it went away, and we went back to sleep on that one, but we'll see.
John, thank you very much.
Thank you.
So the final speaker of this session is Ann Nelson from the University of Washington. Ann was actually a Stanford undergraduate many years ago. She then went to Harvard and worked with Howard Georgi at the very beginning of the exploration of models of physics beyond the standard model. And she's one of these people who has worked on almost every possibility for extensions of the standard model, in many cases contributing really the key innovative ideas in model building. In supersymmetry, she's responsible with Michael Dine for the so-called gauge-mediated supersymmetry breaking. She's worked on models of extra dimensions, models of technicolor. So I think if we're going to talk about the thing that Sid was interested in, the compositeness of quarks, leptons, Higgs bosons, and whatever is out there, she's got all the bases covered, and we look forward to her talk.
And then
forward, backward, and the laser.
Okay, well, thank you for staying for the last talk, and thanks for inviting me. It's I hadn't really, realized until I started thinking about it this week what a amazing thing Slack has been to me over the years. So I went to graduate school on the East Coast at Harvard, and I remember the first time I visited Slack, I was thinking, what is this? These people are trying to understand my talk, and they're asking questions to try and understand my talk because they're curious and interested. And I realized that, that was special. I haven't encountered too many places like that since even. And I think, and people said, well, why is it? And I said, oh, it's Sid Drell. Yeah, he was the heart and soul of this place and instilled a culture here that persists. And it's always been a great place and fun to visit for that reason. So thanks to Sid Drell. Of course, that was my first quantum field theory book as well, my first experience with him. And I've always tried to remember that it's good to be positive and curious and to ask questions if you want to understand something. So Michael told me he wanted somebody who could give the modern view of quark, lepton, and Higgs compositeness. So in order to remind myself of what Sid Drell had to do with this, I went back and reread this classic paper, Brodsky and Drell. And it's actually an amazing paper. There was a lot in it that I hadn't remembered. It was totally read like a very modern point of view with a lot of foreshadowing of things. So this paper concluded that the anomalous magnetic moments of the muon and the electron place tremendous limits on fermion substructure, put the compositeness scale so high we would never have any hope of seeing the excited electrons and muons unless there was a chiral symmetry at the compositeness scale. That is, the left and right-handed muons had different quantum numbers, in which case there was some hope. And it had a lot of thoughts about model building along those directions, so that was really interesting to read about. So the anomalous magnetic moment of the muon in particular would either go like, be linear in the muon mass, or it would be quadratic in the muon mass, and they call that a chirally symmetric model. I think at the very end of this talk, I'll give my estimate for where we should look for that, based on modern ideas about compositeness. And I noticed that, even though apparently Sid was a fan of compositeness, all the papers they found were basically, killing and constraining the idea. It's very hard to come up with a realistic or believable gauge theories in which you have composite quarks and leptons. So nonetheless, we keep trying. This old paper of Ed Tuft has inspired us for a long time, I think 40 years almost, to try and come up with a theory of electroweak symmetry breaking. Tuft said in this paper, probably the best thing to do would be to try and make the Higgs composite and the quarks and leptons composite. And I'll discuss that a little bit further later. So this 40 years is sort of, there's been two aspects to it. One is even trying to find remotely plausible theories with strong dynamics that produce fermions which are much lighter than the compositeness scale. That's very difficult, and you really have to stretch remotely plausible to even come up with that. And then, you can produce theories that you believe might have fermions that are much lighter than the compositeness scale, but to actually get the quantum numbers of the quarks and leptons, the 3 generations out of that, I don't think anyone's actually found anything yet, even now. the key idea to get the light quarks and leptons is to have a chiral global symmetry which is not spontaneously broken by the strong dynamics. That's conceivable. Then you've got to get the right quantum numbers. And the motivation is the gauge hierarchy problem. The weak scale, as we know, comes from the Higgs-Vev. And what should this number be? If you guess it should be some more fundamental scale, well, you think about, well, the next fundamental scale we know about for sure is the Planck scale, which is a lot higher. And so if you try and get the Higgs-Vev out of dimensional analysis using the Planck scale, you find you have to put in a number by hand that's about 10 to the minus 34, which is weird. And so we would like to be able to calculate the Higgs potential. So this is supposed to be a picture of this famous wine bottle type potential that illustrates spontaneous symmetry breaking. This potential has, let's go back. Yeah, this potential just has two terms in it, a quartic term and a quadratic term. And so we'd like to be able to calculate them. And various attempts to do this, I mean, maybe we wouldn't actually calculate the potential from scratch, but we would calculate it in terms of other parameters from some theory which was valid at a higher energy scale, somewhat more fundamental. And maybe it leads you to a theory of everything, or maybe it's just one layer of theory after another, what we call the turtles all the way down type approach. But you know, could we get the next turtle in the step at least by computing the Higgs potential? So one theory that's beautiful that allows us to do this is supersymmetry. However, we've heard about some of its lack of discovery at the LHC. So I'm not going to talk about supersymmetry anymore. Strong dynamics, new dimensions are mostly what I'm going to focus on. And so, like I said, there's no real theory of composite quarks and leptons, even aside the fact that if you had one, it would be experimentally challenging to make it agree with experiment. There's been a lot of activity, a lot of playing. A lot of that activity got very focused 5 years ago when the LHC discovered the standard model like Higgs and hasn't discovered anything else so far, so that the theories that we thought might be promising as natural theories have started to look a little bit less natural, more tuned. I think some people are starting even to murmur about maybe there's a crisis in fundamental physics. There was this week's Economist has an article about how particle physics is facing problems. It says the title of it is Fundamental Physics is Frustrating Physicist, No Guts, No Glory. And it's a long article about all of the, quoting a lot of very skeptical theorists about what's going on in high energy physics theory these days. With every fudge, what were once elegant theories get less so. Researchers are becoming open to the possibility that the truth is beauty argument is a trap and the universe is fundamentally messy. And the article also goes on to talk about how it might be hard for us to get funding for our next accelerators, et cetera. It's really, and then the New York Times this week also had a similar discussion. So, it does look like we might be starting to think about, are we in a crisis situation? But let me, step back from that a bit and say, if there is a continuation of this path that thought we were on towards discovering a more fundamental theory in which we could compute, say, the Higgs potential and understand things from a more fundamental level, I think there's a strong case that it's the so-called modern theories of compositeness that are on that path. The old composite Higgs theories have been revived by, I wrote new ingredients, and then I started to think about, well, what do I mean by new? I mean less than 20 years old. And so these include warped extra dimensions, which I'll explain. This has which turns out to have a lot to do with something called ADS-CFT, which I won't really explain. Also, another idea which, the old idea that the Higgs is a pseudo-Nambu-Goldstone boson has gotten revived by the idea of collective symmetry breaking. And also, the old idea of partial compositeness has gotten revived. So these theories don't meet that old ambitious standard of having the quarks and leptons and Higgs and everything composite, but they do go a step in that direction, and they do make some predictions for things like G-2. So let me remind you, the old composite Higgs idea, Drell-Yan Kaplan in '83, this was a simple idea just based on the idea that there could be something like Technicolor, a strong group, which produced mesons like the pions with quantum numbers which include a electroweak doublet, which we would call the composite Higgs boson. So the Higgs would be something like the kaon of, which is, as you know, an isospin doublet, only now this isospin would be weak isospin. And because these pions are pseudo-Goldstone bosons, they can be quite a bit lighter than the compositeness scale, thereby alleviating some of the issues that Technicolor was facing, that you could raise the compositeness scale relative to the Higgs mass. And in fact, we have a weakly coupled description of strong dynamics for low energy QCD. We can just take that right over and have a weakly coupled description of the Higgs. The weakly coupled effective theory, the compositeness scale, F pi would in this case be quite a bit above the Higgs VEV, and the Higgs would be a kaon in that theory, but with a small VEV relative to its compositeness scale. So a picture of that, of this composite Higgs theory, is that it's something that interpolates between Technicolor and unbroken standard model, minimal standard model, that there's a symmetry which breaks. You've got different possible vacua. Where does our vacua live? Somewhere on this circle? Well, we get to use, so computing the Higgs potential involves trying to compute the dynamics that settle the Higgs on where it's going to live in this vacua. So this is a vacuum alignment problem. The pioneering work on that was Peskin and Preskel, showing how how you can compute the gauge contributions to the vacuum alignment. And also you've got top contributions to the vacuum alignment. And so the idea is that the electroweak scale is proportional to the compositeness scale and a mixing angle, or not a mixing angle, an alignment angle theta. If you make theta very small, you've got the minimal standard model. If you make theta pi over 2, you've got Technicolor, and you can interpolate. But, so that theory seemed appealing for a long time, except they were able to assume that they could put the top contribution to the Higgs potential as a small number, because the top mass wasn't known. In 1983, the theoretical expectation was that it should follow something like the old, I'm not even old enough to remember this, but it was called the rule of 3, which was basically that quark masses differ from each other by factors of around 3. That would put the top mass at around 13. And anyway, so anything higher than, 15 or something was considered pretty radical back then. But we had this shocker in 1996 that the top is actually 174 GeV. The top Yukawa is 1. That means that the top contribution is the totally dominant contribution to the Higgs potential. The top contribution is 7 times larger than the gauge contributions. And the top wants to be heavy. Right? If you look at the alignment calculations, so these are just quantum corrections. So the rule is that fermions have a negative energy from their Dirac C, and it gets more negative if they're heavy. So fermions want a Higgs to have a large VEV. The gauge bosons have a something like a harmonic oscillator contribution to the potential, which would make the vacuum energy go up if they get heavy. So gauge bosons want to be light, but the top wins, and the composite Higgs theory just won't work with this heavy top because it will just push it all the way to Technicolor. So that pretty much seemed to kill that idea, but it got quickly revived a few years later by new dimensions. So a bunch of things sort of happened at around the same time. In the late 90s, 2000, there was, on the string theory side, there was the ADS-CFT revolution, the discovery that a strongly coupled conformal field theory was equivalent to a weakly coupled 5-dimensional theory with gravity, with warp space. And there was the work of Arkani, Hamed, Cohen, and Georgi, which said if you take a 5-dimensional theory and put a lattice in the 5th dimension, then, and it's a finite 5th dimension, then this is actually a 4-dimensional theory, which, you know, it's a renormal, you can have a renormalizable theory if you like, and the, and that theory would have something which they call the little Higgs, which is a pseudo-Goldstone boson, which is much lighter than most of the Goldstone bosons of that theory, so that would allow you to have a much larger compositeness scale relative to the Higgs mass. And then in '99, and continued by this work, there was this amazing conference at the KITP that I was at, and Ed Witten went up and put up a slide and sketched out that the Randall-Sundrum theory is basically a composite Higgs theory, and explained exactly how that would work. He had just sort of, I guess, been thinking about that on the spot, and I'll talk about that. This idea was picked up by several people and eventually used to build what's called the minimal composite Higgs model, which is sort of a marrying of all of these things into what's still, I think, what is a pretty neat picture. So I should explain some of these ideas a little bit more. So Randall-Sundrum is a 5-dimensional theory. The 5th dimension ends on 2 branes, each of which has 3 space, 1 time, 4-dimensional theory. And in the 5th dimension, as you move along the 5th dimension, the scale changes. This is called a warped 5th dimension. So your energy scale changes. So one of these branes, which is 3 + 1 dimensional, it's called the infrared brane, where infrared means about a TeV now. And the other brane is called the UV brane, which, so if you look at particles which are moving around here, the typical energy scale is a TeV, whereas particles which are localized near the UV brane, the typical energy scale is whatever the UV scale is, perhaps the Planck scale. Okay, so that's one of the pieces I'm going to put together in a minute. Let me also go back and explain the partial fermion compositeness. So the partial fermion compositeness, unlike the idea of complete compositeness, turns out to be quite easy to do in a model building way and quite appealing theoretically. So the idea is that you have a strongly coupled theory, and it's quite easy to have a strongly coupled theory with heavy composite fermions. We know about that. I mean, QCD has its baryons. So if we call this strongly coupled theory ultracolor, we'll call the heavy composite fermions ultrabaryons. If some of the ultrabaryons have the same quantum numbers as the quarks and leptons, they will mix with the quarks and leptons. So you just put in the quarks and leptons as fundamental particles, but then our physical standard model particles are linear combinations of fundamental and composite. This is pretty easy to do, and it gives you a neat mechanism for coupling quarks and leptons to a composite Higgs, because the baryons will couple to a composite Higgs, just like the baryons of QCD couple to pions. And then the quarks and leptons of the standard model are actually mixtures of the fundamental fermions and these baryons, partially composite. They will also couple to the Higgs. Okay, so this idea is basically used in the composite Higgs theory, and it's often not recognized as being partial compositeness because this is often described in the Randall-Sundrum language of saying we're going to do a Randall-Sundrum theory and we're going to have the standard model fermions live in the bulk, which means if you have a 5-dimensional theory, you've got standard model fermions that can roam around the 5th dimension in the bulk. But according to our ADS-CFT correspondence, this 5th dimension could be interpreted as a strongly coupled 4-dimensional theory. And fermions in the bulk means fermions which are mixing with the resonances of that 4-dimensional theory. Okay, so then, and this actually marries beautifully with some versions of the little Higgs theory. So the little Higgs theory was based on deconstructing a 5th-dimensional theory, and so the Higgs is a pseudo-Nambo-Gulson boson, just like the composite Higgs. If it was an actual Nambo-Gulson boson, it would only have derivative couplings and have no potential. But the potential for the Higgs, which are couplings that are non-derivative, arise due to terms which break the symmetries explicitly. And if it takes a conspiracy of more than one coupling to break the symmetries protecting the Higgs mass, we call that collective symmetry breaking, we can realize this mechanism of having an extra light Goldstone boson, something we would call the little Higgs. Now, partial top compositeness can easily realize this for the top coupling, thereby reducing that huge top contribution to the Higgs potential. So the idea here is that the top has partners, which are heavy fermions, which partially cancel the top contribution. These are the same as what we previously called the ultrabaryons. Let me sort of give you a picture of the whole thing here. So this is also a picture of the 5th dimension, only now I've put the UV brane at the top and the TeV brane at the bottom. And so we've got some UV scale and some 10 TeV scale I'm going to talk about, and a TeV scale and a 100 GeV scale. So this is sort of the whole, I think, standard picture of composite Higgs coupled to composite fermions, but with the modern ingredients making the theory work and the experiment work. So this UV scale, according to the Randall-Sundrum picture, is at the end of an extra dimension. And then this region here is called the Randall-Sundrum bulk. That's the bulk of the 5th dimension. And the standard model fermions and gauge bosons are free to propagate in this bulk, this 5th dimension. From the point of view of strong dynamics, we have a new gauge group, ultracolor, G. This new gauge group has global symmetries due to the fact that there are multiple flavors, just like in QCD, multiple flavors give us global symmetries. And if we weakly gauge a subgroup of that global symmetry, we will have allowed couplings between the standard model elementary fermions and the strongly coupled fermions. So having the standard model elementary fermions coupled to the strongly coupled fermions is, according to the translation in the dual theory, the same thing as saying standard model fermions live in the bulk. And then we come down to the infrared brane, which is where our composite Higgs theory is said to live. On the gravity weakly coupled side, you just write down a theory with all this stuff on the infrared brane. Partners for the top to cancel the top contribution to the Higgs potential, pseudo-Nambo-Goldstone-Higgs, et cetera. From the point of view of a strongly coupled theory, we've assumed that there's some perturbation of this theory, strongly coupled theory, which triggered confinement without chiral symmetry breaking. That produced some light fermions, which would be the top partners, and then perhaps some additional terms which triggered chiral symmetry breaking, which gave rise to pseudo-Goldstone bosons. That would be our mesons, which would contain our composite Higgs. And then down here below a TeV, we have our good old standard model living on, which has a low energy effective theory containing a composite Higgs, a top partner somewhere at about a TeV. And this theory allows us to compute the Higgs potential. It all comes from the top and the top partners. So I've written here a mass matrix which contains fundamental fermions Q3, which is left-handed, T bar 3, which is right-handed. These heavy baryons, which I've called capital Q bar and T bar. These are vector-like. This parameter theta is the same theta I had previously, which determines the ratio between the weak scale and the confinement scale. So we would like, so if theta is small, the confinement scale, the compositeness scale is close to the weak scale. If theta is pi over 2, then we have something like Technicolor. The heavy baryons don't care what theta is. If we didn't have these other fermions, we would just have a matrix for the heavy baryons whose eigenvalues would be independent of theta. If you were to diagonalize this matrix, you would find degenerate fermions whose masses don't depend on theta. But then when we put in the elementary fermions, we're allowed to put in terms which are consistent with the standard model gauge bosons, which mix the elementary fermions with the composite fermions. We then have to diagonalize the whole thing. And if we write down the quantum corrections from diagonalizing the whole thing, we generate a ultraviolet insensitive potential for the Higgs, which is ultraviolet sensitive, insensitive due to the fact that the square of this mass matrix is independent of the misalignment angle, and so is the fourth power. Okay, so yeah, I just have like 2 slides, don't worry. So we have, so the top Yukawa, arises from this matrix. The top mass depends on these 3 parameters we've introduced here. Other fermion masses can arise in the same way, although their contributions to the Higgs potential are not as important due to the fact that their masses are much smaller. Okay, so back to G minus 2. So when I saw that, I was being asked to talk about, fermion compositeness, and in particular, the Brodsky-Drell paper, which talked a lot about G minus 2 of the muon, I was thinking, well, okay, so what do people say now about G minus 2 in composite theories? And I actually, even in that 700-page review, very few theorists consider the effects of compositeness for G minus 2. And probably that's because there aren't any good theories of a completely composite muon. However, there's this, I would say, the leading contender for physics beyond the standard model, which has a partially composite muon. And so if the muon Yukawa coupling to the Higgs, and if the Higgs is composite, if the muon Yukawa coupling to the composite Higgs is due to partial compositeness, we could estimate G minus 2. So the muon mass, the muon coupling to the composite Higgs would be a strong coupling of order 4 pi, except that the muon isn't actually completely a strongly coupled thing. It just has a mix, which includes a small amount of strongly coupled fields. So the muon Yukawa coupling to the Higgs, mu over the Higgs FeV, is 4 pi times, I wrote it as a mixing angle squared. It's actually the product of a left-handed and a right-handed mixing angle. Let me assume they're about the same. It doesn't really matter. And then the anomalous magnetic moment of the muon you could get by assuming that it comes about the baryon, the ultrabaryon that the muon mixes with has a quite sizable anomalous magnetic moment, would be sort of maximal, like the anomalous magnetic moment of the neutron or the proton, but the muon anomalous magnetic moment gets suppressed by this mixing angle squared. So we take this, this would be the Brodsky-Drell prediction for a very large magnetic moment due to compositeness here. But we get to multiply it by a small mixing angle squared, which turns it into something like the Brodsky-Drell prediction for a composite muon where there was a chiral symmetry, the ultraviolet. So this is basically their prediction, but with a 4 pi here. And then if we just say plug in something like a value of the muon anomaly, which is still consistent with the data, we would find we can limit the compositeness scale to 400 GeV, which doesn't sound all that great. It doesn't sound like a very strong limit. But this is the equivalent of F pi for the strongly coupled theory. This would mean that the baryons of that theory, the ultrabaryons, were heavier, just as the baryons of QCD are heavier than F pi, probably by a factor of about 4 pi. So this is basically saying that we would expect the excited muons, which are actually ultrabaryons, to have a mass about 4 TeV if we had such a large anomalous magnetic moment. Okay, so this is sort of competitive with what you could imagine the LHC might do right now. But I realized that given, this should actually be 16, I think, but it doesn't really matter because this is all squiggles. But given the aims of the G-2 experiment, we could go up quite a bit, limiting it to a compositeness scale of about 2.5 TeV, requiring a very high compositeness scale, which is equivalent to saying the excited muon's mass would be around 25 to 30 TeV. So so the G-2 experiment is actually a very competitive experiment with high energy physics in this context. All right, my last slide. So I just want to say that the composite Higgs theory with partially composite fermions is currently, I would say, the ideal model for thinking about the LHC, given that we have a Higgs discovery, nothing beyond the standard model. I think that's part of the reason why it's so popular. It's a theory which looks nearly standard at the weak scale. Not necessarily any particles beyond those of the minimal standard model, which is a good thing for sort of obvious reasons these days. And it has a parameter you can tune to make it look standard at any energy. You can make the scale of new physics high. However, it's also very flexible at accommodating anomalies. And it allows for deviations from the standard model and Higgs couplings, which is a good thing these days because the Higgs couplings are just entering the era of precision measurement. It provides employment for everybody because if you're formal like ADS-CFT stuff, if you like effective field theory, if you like doing phenomenology, if you like Gauss gauge theory, strong dynamics, whatever, there's something for everyone. Diverse collider signatures, and also diverse low energy experiments. Thank you. Okay.
So in this approach, what experiment will be telling you is giving you bounds on the VEV divided by F, which will be getting smaller and smaller as the experiments.
Yeah, precision electroweak is constraining on that, and that constrains V over F to be about 1/2.
And what about precision Higgs measurements to this point?
And precision Higgs measurements are mostly deviating by an amount on the order of V over F squared. So, so already you wouldn't expect huge precision Higgs deviations unless you extend the model, to have like, I mean, you can have just one Higgs doublet in a composite Higgs theory, but you could also have like a multi-Higgs low energy effective theory, depending on what your high energy theory was. So, but if it was just a single Higgs in the low energy effective theory, precision electroweak already, I would say, constrains the compositeness scale to be 500 GeV, which would constrain deviations in the Higgs couplings to be sort of 25% or smaller.
Yeah, but you also have to put searches for top partners and things like that.
Right, so the top partners tend to be pretty heavy in these theories. So the top partners tend to have couplings which are proportional to these new Yukawa couplings. I don't know if you remember them, lambda 1, lambda 2, lambda 3 times F. The top Yukawa coupling, which is 1, is proportional to the product of all 3. So all of these Yukawa couplings are fairly big, at least 2. So it's pretty hard to get any top partner lighter than a TeV. Yeah.
To what would a heavy heavy muon partner decay? Suppose you produced it in pairs at CERN.
Yeah, well, it would be very heavy, right? It means, and it could decay into, okay, so if there's a technibaryon number which is conserved, or an ultrabaryon number which is conserved, it might not decay depending on if it's light, in which case it would decay to, it could decay to like whatever the lightest ultrabaryon was plus weak gauge bosons or something like that. Or if it was the, or if the lightest ultrabaryon was electrically neutral, it could decay to that plus a W or something like that.
So, Anne, thank you very much. Let's thank all the speakers in this session. And let's take a 25-minute coffee break. I'm sorry we're running so late, but there is a reception after this, which there's still time for. So come back at 4:25.